Live. It looks like we are live. All right, so this lab shouldn't cover anything new. I know I've already covered these sorts of reactions in class. I didn't use the term double replacement, but that's because I'm a good person rather than some sort of deviant. All right, so all that's happening is you're mixing two salts, here AX and BY, and they swap their partners, hence double replacement. Okay. Then you're going to get, those new partner ions, those new salts, and the question is, will you have soluble or insoluble products? So, the stuff you've already covered in class. Really quick, the solubility rules. The things that are always soluble are the alkali ions and ammonium, and NO3 minus, ClO4 minus, that's perchlorate, and acetate. Okay. There are a number of different ways of writing acetate, of course. You can also do, let's see, CH3COO 1 minus, or you can just do AC 1 minus. All right. So no matter what these guys are paired with, they will always be soluble. Just a quick reminder, when I say alkali, I'm talking about these guys. This first column of the periodic table, those are the alkali metals. And they form a 1+ ion. So if you see one of those guys in a salt, they will always be soluble. Then we have usually soluble. These guys prefer to remain dissolved in solution, but sometimes they don't. So first up, we have chloride, bromide, and iodide. Typically soluble, but if they are partnered with one of these guys, they will not be. So their exceptions are silver, which is always a 1+ ion, mercury 1, that's Hg, 2+, and finally, lead 2. Okay. Partnered with any of those, the result will be insoluble. And also usually soluble, we have sulfate. Likes to dissolve in water. Sometimes it doesn't. It will remain undissolved when partnered with strontium, barium, mercury 1, or lead 2. And finally, we have the ones that are usually insoluble. They prefer to remain out of solution. Okay. Our first group is carbonate, that's CO3 2-, and phosphate, PO4 3-. They prefer to remain out of solution, but they will go into solution. They do have some exceptions. Their exceptions are the alwayses. If they are paired with an always soluble ion, then they will dissolve. And finally, we have sulfide and hydroxide. They prefer to remain out of solution. They will dissolve for the alwayses, and they're a little bit more forgiving because they'll also dissolve for calcium, strontium, and barium. All right, so those are your solubility rules. Okay? It pays to remember those because you're going to need those for this lab and also for the test you took this past week. All right, so when you mix your salts, they are dissolved in water. That's what it means for and their ions, I should say, are separated. That's what it means for a salt to dissolve. Okay. Insofar as it can dissolve, that means that the ions are separating. So we call it dissociation as opposed to association. They're splitting up. So, for example, let's do calcium chloride. Okay. You dissolve that in water, and then it's going to split up into calcium ions and chloride ions. Okay. That's what it means to be dissolved. And we represent that with, we have a solid, and then we throw it into water, and it breaks up, and now these guys are aqueous. Okay? Aqueous means just dissolved in water. So, when you mix your salts, you may or may not get an insoluble product. So let's say we mix calcium chloride, aqueous, with silver nitrate, also aqueous. Okay? We know it's aqueous because nitrate is one of the always soluble ions. So they're going to swap partners. You're going to end up with calcium. Okay, we're going to need 2 of these. Nitrate and silver chloride. Now, we go back to our solubility rules. Nitrate is always soluble, so this guy is aqueous. Chloride is usually soluble, but silver is one of its exceptions. So that is a solid. Now this here is what we call the molecular equation, because we are presenting the salts as if they were molecules. Okay? But they're not. Okay, first off, they're ionic compounds, which don't have molecules. Also, these guys are dissolved in water, meaning that they have split up into their constituent ions. So from there, we can present it as an ionic equation in which everything that is dissolved is going to be broken up. So calcium, 2 plus 2 chloride ions, plus 2 silver ions, plus 2 nitrate ions. It's going to split up, and I'm going to put the reactants down here because I'm out of room. Calcium 2 plus 2 nitrate ions, plus silver chloride. Okay, the silver chloride is solid, so it's not dissociated, so we don't split it up. Everything else, though, is aqueous. Now, you'll notice that calcium and nitrate haven't changed. They haven't done anything. They have remained in solution. So they're not actually doing anything in this reaction. Okay? They are what we call spectators, or spectator ions. Okay? They're just watching the reaction. They're not participating. Therefore, we don't actually care all that much about them. So what we do is anything that remains the same on either side of the arrow, we get rid of it. All we care about is the stuff that's actually participating in the reaction. And so that means that what we're left with now will be our net ionic equation. Basically, Ag plus Cl minus is going to AgCl. AQ, AQ, solid. All right, so that is how you draw out these reactions. Molecular, ionic, net ionic. So you're going to use the solubility rules to predict whether or not a reaction will take place. And then from there, you'll draw out the ionic and net ionic equations. And I believe that's all you're going to have to do for this particular lab. Oh, wait, no, there's also going to be a prediction matrix. Okay, can't forget about that. All right, so you are going to be, let's see, mixing a bunch of different salts, and you'll be predicting the results of those mixings. So let's say just, all right, I don't know what salts they're actually going to give you, but let's say silver nitrate, calcium chloride, let's go with sodium carbonate, and let's make a fourth one. How about potassium hydroxide? There we go. Okay, so when they say a prediction matrix, what they mean is, okay, what happens if you mix silver with nitrate, silver 1 plus I should say, carbonate, chloride, or hydroxide? And what happens if you do... Oh, actually, no, that's not how they're going to want you to do this. Okay, so silver nitrate. What happens if you mix your silver nitrate with sodium carbonate? calcium chloride, or potassium hydroxide. What should you see? Should you see some sort of soluble or insoluble product? And then potassium hydroxide. What happens if you mix that with sodium carbonate or calcium chloride? Finally, calcium chloride. Okay, what happens if you mix that with sodium carbonate? Okay. So drawing it like this, you get this sort of step shape. They might give it to you, with these guys on this side, and thus it'll be reversed, but it's going to be the same sort of thing. But this way, you get to compare every salt with every other salt. Silver nitrate, 1, 2, 3 comparisons. Potassium hydroxide, 1, 2, 3 comparisons. Calcium chloride, 1, 2, 3 comparisons. All right. And thus you would look at the solubility rules for all of these guys and say, would you get an insoluble product? Yes, you would get, let's do it. Here you would get silver carbonate. Here you would get silver chloride, and here you would get silver hydroxide. All three of those would be insoluble products. Potassium hydroxide, sodium carbonate, no. You would not see any reaction there. Okay? No reaction, because potassium carbonate is still going to be solid, and sodium hydroxide would still be soluble. And then these guys, calcium hydroxide, nope, that's also soluble. So you're going to get no reaction there as well. And then calcium chloride plus sodium carbonate, you would see a reaction there. You would get an insoluble product. You would get calcium carbonate. So that is what they're talking about with a prediction matrix. You would see reactions in some of the cases, and you would get no reaction in other cases. And so what you would then do is you would actually have a collection of, in this case, 4 solutions, and you wouldn't know what was in them. You would test them against each other, A, B, C, and D, and you would then conclude, well, A has got to be this one, and B has got to be this one, and C has got to be this one. And you would, and D would have to be this one. And you would know which was which because of the way they interact with one another. Although in this case, I chose this poorly because you would have no good way of distinguishing the sodium carbonate and the calcium chloride. doesn't matter too much. But the silver nitrate would be immediately obvious, as would the potassium hydroxide. All right, so that is what you're doing in this lab, is you are going to do those double replacement reactions. And then you're going to make a prediction matrix, and then you're going to actually figure out what these various unknown doohickeys are by comparing the results of the mixtures of when you mix these unknown compounds. And you'll compare the results of those mixtures with your prediction matrix. Okay, that's it for this lab. I will see you next week, perhaps, some Egyptians believe.